Hey everyone, and welcome. Today we're diving into the incredible technology that allows the digital world to literally reach out and physically change our reality. Let's get right into it.
So just think about it for a second. How can a few lines of code actually lock a door or adjust the temperature in your house, or even help a surgeon perform a delicate operation? That's the big question we're going to tackle today. How does the digital world actually touch and change the physical one?
Well, the magic really begins with this unassuming but absolutely essential component, the transducer. You can think of it like a universal translator for energy. It's this clever little device that takes energy in one form, say physical motion, and just flips it into another, like an electrical signal. It is the bridge between the digital and physical worlds.
Now, transducers basically come in two main flavors. On one hand, you've got sensors. Think of these as the senses of a system. They feel things like heat or see light, and they turn that physical information into an electrical signal. And on the other hand, you have actuators. These are the muscles. They take that electrical signal and turn it back into real-world action. So one is listening and the other is doing.
For now, let's focus on those muscles, the actuators. And we're going to start with the established powerhouses, the industrial workhorses that have been doing the heavy lifting for decades. Let's meet the heavy lifters.
The whole process is actually pretty elegant. You've got a digital processor, the brains of the operation, that sends out a control signal. That signal goes to an actuator, which converts the electricity into energy, and that energy creates real mechanical motion. And just like that, a command in software becomes a tangible action in the real world.
All right, first up, hydraulics. When you need to move something seriously heavy, this is what you call. By using compressed fluids, hydraulic actuators can generate just a massive amount of force. We're talking about heavy industrial machinery, the giant arms on an excavator, or even the landing gear on a passenger jet. Next, we've got pneumatic actuators. So instead of liquid, these use compressed air or gas. And because of that, they're incredibly responsive and a bit more, well, compliant. They're perfect for things that need quick, snappy, repeated actions. Think vehicle air brakes or the control valves you'd find all over a factory floor.
Then there are electric actuators, and these are, well, they're everywhere. I mean, from consumer robotics to the tiny little motors that make your phone vibrate. They're super efficient because they turn voltage directly into mechanical torque, which makes them clean, fast, and pretty economical to run.
And finally, we have mechanical actuators. You can think of these as the fundamental building blocks of motion. They use simple things like gears, rails, and pulleys to change one kind of movement, like something spinning around, into another, like something moving in a straight line. The steering in your car is a perfect example.
Okay, so this chart right here, this is where it all clicks into place. You can see the trade-offs so clearly. Need raw, uncompromising force for heavy lifting? You go hydraulic. Need that quick, responsive action for something like brakes? Pneumatic's your answer. Looking for clean, cheap, and fast motion for robotics? Electric is the way to go. And for just fundamental motion conversion, you have mechanical. Every single one is a specialized tool for a very specific job.
Okay, we've seen the seasoned pros, the industrial workhorses. Now let's jump to the absolute bleeding edge. We're about to enter the world of smart materials, where the line between what a material is and what a machine does starts to get really blurry. This is where we stop building machines with materials and start creating materials that are the machine.
Get this, shape memory alloys, or SMAs for short. These are literally metals that have a memory. You can deform them, but once you apply a little heat or a magnetic field, they snap right back to their original, remembered shape. And the craziest part? They do this with zero electricity, and they pack a huge amount of power for their tiny size.
Then you have soft actuators. These things are made from stretchy polymers that can create these really gentle, muscle-like movements. And this is a total game changer for anything that requires, a delicate touch. We're talking about a robot that can pick fruit without bruising it, or the super precise tools used in robot-assisted surgery.
And if you thought that was cool, we can take it even one step further with shape memory polymers. Now, just like the alloys, they remember a shape. But these can respond to even more subtle triggers, like a change in pH levels, or even just being hit with a specific frequency of light. Just imagine a material that could heal its own cracks when you shine a special light on it. It's wild stuff.
So you've got the big, powerful workhorses on one hand, and these mind-bending, futuristic materials on the other. So how in the world do engineers decide which tool to use? And how does it all come together to finally close that physical-digital loop we started with?
Well, it really all boils down to a balancing act every single time.
An engineer has to look at the job and weigh all the options, from weight and power to torque and stiffness. Are you building a small drone where every gram matters, or are you building a massive factory arm where you need all the power and stiffness you can get? Getting that balance right is absolutely everything.
And here it is. This is the whole thing in action, the complete loop. You have a physical event, let's say a fire starts. A sensor detects it. That data gets zapped over to the digital brain, which makes a split-second decision. Then it sends a signal back out to an actuator, maybe an electric valve, which takes physical action and puts the fire out. It's this continuous self-correcting conversation between the physical world and digital intelligence.
Okay, so if you're going to take away just a few things from all this, here's what they should be. First, simple but crucial. Sensing is the input, actuation is the output. Senses and muscles, remember? Second, there's a huge toolbox out there, and you have to match the right tool to the job. Third, these systems aren't magic. You always have to account for small errors. And finally, number 4, it's always a balancing act between trade-offs like power, weight, and speed.
So at the end of the day, what does this all mean? It means the line between the physical world and the digital world, it's not just blurry anymore, it's dissolving. Through this elegant loop of sensing and actuation, they're becoming locked together in a continuous, programmable dance. The only question left is, what are we going to teach them to do next?